we are now going to go full length into the new topic, which is discrete Fourier transform. We're going to move from discrete Fourier series to discrete Fourier transform. This is DFT. Okay. So what we want to summarize is that we have a finite length sequence x of n. Finite length sequence x of n. And this x of n is non-zero in the range is non-zero in the range n greater than or equal to 0, less than or equal to n minus 1. So basically it has got a length equal to n. Okay. Now we can always append zeros if needed. Can append zeros to increase the length. So basically you can work with length n, or if you want to increase the length, supposing if you want to increase length to a value m, then we have to append m minus n zeros. Okay, that's so basically you can always append zeros. Now with this we can now connect it to a periodic signal. Let's call it the associated periodic signal. Associated periodic signal is x tilde of n, and this is produced by convolving with a impulse train which is spaced n samples apart. So basically this is r equal to minus infinity to infinity x of n minus Rn. You're basically repeating the sequence x of n with a spacing of n. And remember, if you choose n sufficiently large, you will not get any overlap, and that is what we want to establish here. Now, if you have x tilde of n, you can get x of n. If you have x of n, you can get x tilde of n. How do we get that? X of n is one period of the periodic sequence. This is equal to x tilde of n in the range n greater than or equal to 0, less than or equal to n minus 1, and is equal to 0 otherwise. Okay. Now, important to note that x tilde of n is a infinitely long sequence. It has got samples in the range 0 to n minus 1. It has got samples outside of n. Now, supposing I get a value of n which is not in the range 0 to n minus 1. What sample does it map to in terms of x of n? That is very, very important. So basically we say that any x tilde of n can be interpreted, because of the periodic nature of x tilde of n, as some sample in the range 0 to n minus 1. And what will be the value of that sample? It will be n modulo uppercase n. Okay, so basically if it was value equal to 1, it remains as 1. If it was minus 1, then you say minus 1 modulo n is nothing but n minus 1, and therefore that is how it will be, that will how be interpreted. And what is the notation that is used? Very important, because when you read the book, you will see this notation quite often. Double bracket, the variable n and the index for the modulus. Okay, the modulus index. So the uppercase n. So basically once you do this, double bracket n, this is belongs to the samples in the range 0, 1 through n minus 1. So it will, there are no because of the modulus operation. So this is the modulus operation, modulo operation. And therefore this is our representation that we will get. Okay, so x of n is a finite length sequence, and what we say is that x tilde of n has got a discrete Fourier series coefficient which is given by x tilde of k. Now, what we are interested in is the representation of x of n, not x tilde of n. So, therefore, we will choose one period. Okay, here is the key result. So, choose the Fourier coefficients which are obtained from one period of x tilde of k. Choose the Fourier coefficients from one period of x tilde of k. Period of x tilde of k. Okay, what do we mean by that? Let's write that down. We are saying that we are interested in x of k, which is equal to, just like we did for the periodic signal, this will be equal to x tilde of k for k in the range 0 through n minus 1 and will be 0 otherwise. Okay, so what we are doing, x tilde of n, we take one period and call it as x of n. X tilde of k, the Fourier series coefficients are also periodic. We take one period and call it x of k. Okay, now here is the key result. What is the discrete Fourier series relationship? The synthesis equation, the analysis equation. The analysis equation is x tilde of k is given by summation n equal to 0 through n minus 1 x tilde of n w n k n. And the synthesis equation, x tilde of n is given by 1 over n summation k equal to 0 through n minus 1 x tilde k, uppercase x tilde of k w n minus k n. Okay, so this is the DFS relationship. Now, the corresponding DFT relationships. Okay, very, very important. We have derived it from here. The corresponding DFT equation, we say that, okay, here is the analysis equation of the DFT. DFT. X of k is equal to summation n equal to 0 through n minus 1 x of n w n k n. Exactly the same as this representation. However, we also specify that this is equal to 0 for this is in the range k equal to 0, 1 through n minus 1. This is in anything outside of this range, the DFT coefficients are 0. Similarly, x tilde of n, we say that is equal to 1 over n, just like we have the synthesis equation for the DFS. We have the synthesis equation here. Let's call this the synthesis equation. Summation k equal to 0 through n minus 1 x of k w subscript n minus kn, and this is in the range n equal to 0 through n minus 1 and will be equal to 0 otherwise. Okay, notice that we have a very, very similar relationships. So, we now give the notation as x of n having the discrete Fourier transform DFT relationship given by x of k. And we can also say that this is the forward transform. Okay, and in the reverse transform is called the inverse DFT, IDFT. Okay, so this is what we call as the inverse transform, and this is the forward transform. Okay, very, very important. Now, we can study DFT without getting into too much of thought about the underlying discrete Fourier series. However, every property that we look at for the discrete Fourier transform relies on the underlying framework that is produced by the periodic signal x tilde of n and the discrete Fourier series coefficients DFS. So here is the thought process that we want to have. Focus on the DFT. Okay, our focus is on the DFT. I have a finite length sequence. I represent it in terms of the DFT, which is also a finite length sequence x tilde x of k. Okay. Now, what we need to keep in mind is that there is the underlying periodicity. It's not explicit here. There is the underlying periodicity. Where does this periodicity come from? From the fact that x of n is related to a periodic signal x tilde of n. Okay, this x tilde of n has got a relationship to x tilde of k, and this has got relationship to x of k. Okay, so we want to relate x of n and x of k, but in the middle there is a you can think of it as something that's not explicitly visible, but underlying it is very much a part of our thought process. Okay, so that is why we are able to say that anytime you get an index which is not in the range 0 to n minus 1. So for example, even here, if you want to say x tilde of k, k can be within the 0 to n minus 1, or it can be outside. However, when it maps to the DFT coefficients, it must be only in the range 0 to n minus 1. Okay, the same as uppercase X, double bracket, K, close bracket, subscript n, modulo n. That modulo representation, so the index of x of n and uppercase x of k, that has to be defined in the range 0 to n minus 1. That is extremely important. Now, what comes after this? After this comes the properties of the discrete Fourier transform. Okay, so the properties of the discrete Fourier transform. And this is summarized for us in table 8.2. What I would like to encourage you to do is to look at table 8.2 and start to work with some of the properties that are there. So let me just quickly summarize for you a couple of properties. First property is the property of linearity. Okay, when it came to the discrete Fourier series, we said that we are dealing with periodic signals. Both signals must be periodic with period equal to n. Now, in this case, we have a slight relaxation of that condition because we have finite length sequences. And remember, we can always append zeros. So, if I have x1 of n and x2 of n, I can always append sufficient zeros such that both of them are of the same length. So, basically, we can say that when you are combining two finite duration sequences, x1 of n and x2 of n, finite duration sequences. Okay, we call them as x1 of n and x2 of n. Okay, they can be of different lengths. The advantage is that we can append zeros so that we are now having the same length. Okay, so append zeros to make them of the same length. Okay, let that length be equal to n. Okay, so originally they may have had n1 and n2, but we want to add zeros such that basically you can So we can choose n to be equal to the max of n1 comma n2, and you can always add zeros to the sequence that is shorter in length. Of course, you can choose something even larger than this, but at a minimum it should be the maximum of these two. If you have chosen in this fashion, then x3 of n, which is equal to alpha times x1 of n plus beta times x2 of n. So we are now saying that we have DFT relationships for x1 of n. This is the DFT of length n, not n1 or n2. It is the length which is the common length, and this is equal to x1 of k. Okay, similarly, if you have x2 of n, which has got a DFT of length n equal to x2 of k. Now, given these two relationships, the property of linearity says if I form a linear combination of these two signals, then the corresponding discrete Fourier transform, the transform domain representation of this finite length sequence, can be obtained as alpha times x1 of k plus beta times x2 of k. Very powerful result. Just like we had it for the discrete time Fourier transform, we had it for the Z transform, we had it for the discrete Fourier series. Now we have it for the discrete Fourier transform. And so what we are saying is both sequences must be of the same length. The DFTs must be of the same length. Once you have the common length, then you can do linear combinations of these signals. This is the property of linearity. Then comes the property of circular shifts. Okay, the next important thing is the property of a circular shift. A circular shift. Now let us look first at a circular shift in time. Circular shift. So basically, just for reference, let us look at what is the corresponding relationship for the discrete Fourier series. If I have x tilde of n with the corresponding DFS given by x tilde of k. So let me just write it down. This is a discrete Fourier series relationship. Then we know that x tilde of n minus m. This gives us a result which is the original DFS coefficients multiplied by a complex scale factor. Wn km. Okay, Wn km. Okay, it depends on m, it depends on k, which depend with the corresponding DFS coefficient. So this is also a DFS relationship. Now, how do we get the corresponding relationship for the discrete Fourier transform? So basically, here is the problem statement. We are given that x of n has got a discrete Fourier transform representation which is given by x of k. Now, if I want to look at the DFT coefficients given by e power minus j 2 pi by n mk times x of k, what is this equal to? Okay. Now, you can say that x of n is derived from x tilde of n, x of k derived from x tilde of k. So there is probably a tendency to say, oh, I think this is going to be equal to x of n minus m. Am I right? Because x of n is one period of x tilde of n. If the corresponding x of x tilde of k multiplied by this complex exponential relates to x tilde of n minus m, this should also be. The answer is almost correct, except that this n minus m may go outside the range of 0 to n minus 1. Supposing you substitute n equal to 0, then you get a negative value. So what should this be equal to? This should be interpreted as n minus m modulo n. Then you will have the correct answer. Okay. So if you call this as the sequence x1 of k, and then say that the corresponding sequence x1 of n, which has got the DFT coefficients, which is corresponding to x1 of k, then x1 of n is equal to x of n minus m modulo n. Okay. So basically, how did we get the answer? We looked at what was the behavior of the discrete Fourier series or the periodic signal, and then we said, okay, no, but we can only consider values in the range 0 to n minus 1, and therefore applied the modulo relationship. Now, this is the method by which we will develop the properties of the discrete Fourier transform. And so what we see here, what we've seen today is a foundation for looking at whenever you have a need to interpret a particular result, then you look at the corresponding DFS relationship and then come back to the DFT relationship and then obtain the final result. So this is the good introduction for the topic of discrete Fourier transform. What I would like each of you to do is to go through Oppenheim-Schafer chapter 8. If you go back and look at the topics, we have covered all the things that are needed for 8.5. and started to look at 8.6. So if you can read up sections 8.5 and 8.6, then next session we will complete 8.6. We will complete an application, which is the application in linear convolution. Remember, linear convolution is the same as circular convolution with sufficient number of zeros appended. So we will now look at how to do circular convolution, how to obtain the result of linear convolution, and that's going to be an important application. And then we will look at several examples, and then finally we will ask the question, what is the most efficient implementation of the discrete Fourier transform? And that will be, the answer will be the fast Fourier transform. So that is our plan that we will complete in the next session. Thank you.